Alright, so in this video I'm going to be explaining this important paper with the title Diffusion Schrodinger Bridge Matching. This NeurIPS paper in 2023 by Oxford University. I have seen papers of Campbell in 2022, Andrew Campbell in 2022. In 2024, he has written the two diffusion papers, and this is another paper from him. Very good papers that has received many citations. Because the idea is beautiful, terminology is very good, everything is very good in his work. So solving transport problems, for example, finding a map transporting one given distribution to another, has numerous applications in machine learning. Novel mass transport methods motivated by generative modeling have recently been proposed, like denoising. I have a playlist for denoising score matching, not denoising diffusion models, but I have a playlist for flow matching models. So they have recently been proposed and implement such a transport through a stochastic differential equation or an ordinary differential equation. For example, if you use flow matching, we use ODE. For SDE, the reverse one is we use for diffusion. And however, while it is desirable in many applications to approximate the deterministic dynamic optimal transport map, which admits attractive properties, DDMs, denoising diffusion models, and FMMs, flow matching models, are not guaranteed to provide transports close to the optimal transport map. In contrast, Schrodinger bridges compute stochastic dynamic mappings, which recover entropy regularized version of optimal transport. Unfortunately, existing numerical methods approximating stochastic bridges either scale poorly with dimension or accumulate because it's a stochastic, it's a entropy regularized optimal transport. So we introduce iterative Markovian fitting, a new methodology for solving this Schrodinger bridge, SP Schrodinger bridge problem. They use iterative Markovian fitting and diffusion Schrodinger bridge matching, a novel numerical algorithm for computing IMF iterates, this iterative Markovian fitting, which we call it IMF. DSBM, this Schrodinger diffusion Schrodinger bridge matching significantly improves over previous Schrodinger bridges numerics and recovers special or limiting cases. So let's see what it is. So when we say bridge matching, it covers flow matching, it covers also denoising diffusion. So you see here a comparison between iterative Markovian fitting and iterative proportional fitting. IPF is iterative proportional fitting, IMF is iterative Markovian fitting. So the Schrodinger bridge is unique probability such that this probability of source is pi0, probability of target is pi t, which are simultaneously by proposition 5. So let's see. Schrodinger bridge is a dynamic version of entropy regularized optimal transport. So we denote by P of C the space of path measures. And you know this Markov kernel and probability measure mu. These are the background that you need. And we have mixture of bridges. If we write like this, it's a mixture of bridges. So when we say pi It means the integral, when you integrate over all of these mixture bridges. Denoising diffusion models are a popular class of generative models. They define a forward noising process using STE on the time intervals 0 and t. And this B is a Brownian motion. You see this Brownian motion in physics, in financial mathematics, everywhere, in stochastic control theory. And this is a simple one because with drift and diffusion, this drift part is very simple. It's constant and 1 over 2x of t. So it's linear in terms of x. And this one, there is not state dependent. It's not related to x, so it's just pure Brownian motion. So the diffusion converges toward the stochastic standard Gaussian distribution. Because it's very simple. We know the solution of that. It converges as you increase the time, then it becomes more and more like a normal distribution with mean zero and identity variance. A generative model is given by its time reversal. So dy is the reversal. So an alternative to consider time reversal of forward noising process is to build bridges between two distributions and learn a mimicking diffusion process. This approach generalizes DDMs and allows more flexible choices of sampling process. We call this framework bridge matching. This paper is very important. It explains many deep concepts that unifies many ideas. So this pi of t is the data distribution because at time t you reach the data because you are doing the reverse. And so we have this q, the pass measure associated with this process. Now consider a distribution of this process pinned down at an initial x0 and terminal xt. So you fix it. Under Moyle assumption, this pinned process is a diffusion process, like diffusion, that Brownian bridge. So at that time, we know that at this time reaches this point. So we fix that's why it uses the word pin. Pin, it means fixing something, like initial point and the last final point. We fix it. Now, we define an independent coupling, which is pi 0 and pi t. And this path measure is a mixture of bridges. We aim to find a Markov diffusion on 0 and t, which admits this marginal that we are interested. For such V, a generative model for sampling data distribution is obtained by simulating Y. It can be verified that indeed Y of t, which we sample from pi, we present the theory behind the idea more formally using Markovian projection. So we do not in practice have access to VT star, therefore we learn it. These are the basic things that you know from this flow matching, also this idea. We call it Markovian projection in section 3.1. Later we will see. So here, now, Q is a Brownian bridge. So the regression loss that we designed, this is the regression loss. For example, for flow matching, we learn V theta, the velocity. Here the regression loss is very simple. You learn the velocity that you want to learn should mimic this kind of velocity of true. and letting sigma goes to 0, we recover the flow matching. So when sigma, when you have very low noise, so the weight of the noise, let's say sigma t be the weight of the noise, is very small. If it is very small, it goes to 0, it means nothing. So it becomes very deterministic. Then it becomes completely flow matching. So that's why it's bigger than this Brownian. This becomes bigger than any flow matching or diffusion. I mean, it covers the paradigm of flow matching, because flow matching is a special case of that. So the Schrodinger bridge problem, which is a very old idea, in 1932, Schrodinger is the same physicist who worked in quantum mechanics, and we have a PDE for that to solve the Schrodinger, that probabilities of quantum states. So it consists in finding a path measure. This path measure, this, for example, path integral of Feynman, if you have studied quantum field theory, then you realize how beautiful it is. So this probability of Schrodinger bridge is arg mean of KL divergence between P and Q, that P is your source and target is pi of t. So Q is a reference path measure. In what follows, we consider Q defined by the diffusion process, which is Markov, and without loss of generality, we assume Q0 is pi 0. So the property of this Schrodinger bridge is that it can be defined as a mixture of bridges. So here we know this is the entropy, and we want to minimize the arg mean of expectation of x0 minus xt. The only thing is that we have added this entropy, and pi is the solution of the entropy regularized optimal transport. So the Schrodinger bridge can also be obtained using the following problem. I mean, theoretically, we can do this. Then P is given by STE drift. So for sigma is equal to 0, as I said, it recovers the optimal transport problems. So one way to solve this equation 6, this arg mean of KL, one way is this iterative proportional fitting method. Because it does it sequentially. You have a sequence of path measures, pi tilde, it 2n plus 1 is related to 2n. So it's very iterative process. But because any iterative process, it needs an initialization which we set to Q. So this procedure alternates between projections in the set of path measures with given initial distribution pi 0 and terminal distribution pi t. It can be shown that pi t, p tilde are associated with diffusions, and that for any n is the time reversal of p tilde 2n. So this is just a method, iterative Markovian fitting, Markovian projection and reciprocal projection. Projecting on Markov measures is a key ingredient in our methodology and in bridge matching framework. This concept was introduced multiple times in the literature in 2022, also very old, 1986. So we focus on Markovian projection of path measures given a mixture of bridges. So here they define a Markovian projection of pi with this associated ST. This is the Markovian projection of pi. Sigma v, the v here is the sigma to expectation of gradient of log q. So flow matching can be recovered as the deterministic one. When you say, as I said, if sigma goes to 0, if it is very small, then it becomes, the flow matching is just a special case of that. So it's very beautiful theoretically as well as practically, because we want to generalize flow matching as well. So while the Markovian projection ensures that the obtained measure is Markov, the associated bridge measure is not preserved in general, because the projection is not equal to measure. Projection of pi is not equal to q. So measures the same bridge as q are said to be in its reciprocal class. So pi is in the reciprocal class of q. So we define the reciprocal projection. So they have the proposition that if pi star is that projection, then that pi star, that means the projection of P, is the KL argmin of the KL P, P and pi. So it's an iterative process, as I said. So after this iterative process, we get our Schrodinger bridges. Now we present diffusion Schrodinger bridge matching, which is a practical algorithm for solving the Schrodinger bridge problem obtained by combining IMF procedure with bridge matching. IMF alternatively projects on the Markov class and the reciprocal class. So we first sample this initial and terminal and target from the joint distribution, then sample from the bridge. After that, we sample from the bridge. So the bottleneck of IMF is in the computation of the projections. But because we know proposition 2, so we can just solve it like this. We know what theta star is. So the real algorithm for diffusion Schrodinger bridge is very simple. You have your input is just the joint distribution and also the tractable bridge. Also, you need the number of outer iterations, n. So because we have n, the number of outer iterations, so we go through it. We learn v phi star, then we go through m, then this iterative process that I said is here. Then again, we learn for, instead of phi star, we have theta star. So the output is v of theta star and v of phi star. So an equilibrium of DSBM is a time reversal given by 9 and are both associated with optimal Schrodinger bridge path measure. So a probability flow Z star is this. You can find it like this, which note, however, that the path measure does not correspond to P star. In particular, Z0 and ZT is not an entropic optimal transport plan. However, since for any t, Z star has marginal distribution, we can compute the log likelihood of the model. Flow matching and conditional flow matching. In conditional flow matching, flow matching is very simple. You just want to learn v theta. The expectation is over pi. But in conditional flow matching, Now, the only difference between